What's up, gang? Hey. Let's go!
What?
Argonia test launch. Take one. Okay, she's on.
Let's go. Okay. Beeping. There we go. Okay. Godspeed, rocket. Argonia test launch in 3, 2, 1, ignition! I am Benjamin Smith. I am the team lead for Argonia. I do a lot of the behind the scenes work with getting order forms sent out, scheduling, working with a lot of manufacturing, final decisions for designs, and a lot of budgeting for the competition itself. There's a few ways that we can go behind actually giving the goal of the rocket. The easiest answer is to have a successful rocket launch in the competition and obviously go for gold. With this being still our first steps for competition and multiple stages overall, we really want to make sure that we're getting the basics, have that information documented for future members that will be in our positions to know what we did so they can learn from our mistakes. With the current simulations of flight on an open rocket, max altitude is just about 17,000 feet. Max acceleration is just over 5.5 Gs, with max velocity being just about 630 miles per hour. That'll be at motor burnout of the booster section, where that's just about 8.5 seconds after 8.5 seconds of burn time, second delay for separation, and then second delay for motor ignition, with that all happening within the first 13 seconds of launch. And the full dimensions of the rocket, internal diameter of the rocket is 2.5 inches, with the full length just being 9.25 feet long, with the booster section being 44 inches long, not including the coupler that mates with the sustainer motor section. The rocket's weight with motors is just about 18.5 pounds, with no motor being just over 10.5 pounds, with chutes that's corresponding with those weights being 7-foot chutes. Depending on the weight of full burnout, including the casings for the motors, it'll be sitting around 15 to 20 miles per hour descent rate, with the sustainer being faster coming down to the weight of the golf balls. Both descent rate within margins for the competition. The stability of the rocket, with it being just the boat of transonic and 2 stages, we decided to have a little overstable with those characteristics for those rockets, with it being 2-stage combined, 2.86 stability with both motors, and with just the sustainer section being about 1.5 stability.
So the main thing that we did for the propulsion team, we selected the motors for our rocket to maximize our score along with the payload. And we picked them due to their burn characteristics, and then we also created the mounting system for the rockets. We ended up going with the J140 and K300 motors. The total impulse for our rocket is 3,754 Newton seconds. It was the maximum amount of force that we could have, and so it was modulating how much force we wanted where in the launch profile. We ended up choosing that number through a combination of the motors that we selected, and that came down to wanting to maximize the power that the rocket has while minimizing the impulse because of the way the scoring equation works. We have a checklist of operations to prevent any malfunctions or any malpractice, and the propulsion lead, myself, and our team lead, Ben, are going to be in charge of mounting and loading the motors to maximize safety. For the actual retention and alignment portion of our motors, we had some specially constructed carbon fiber bulkheads and centering rings that we were using to withstand the loads of the motors, and those are really in place to prevent any vertical or horizontal blowouts and to keep the motors aligned in the rocket. That really helps maximize our safety factor.
My name is Connor Mispagel. I am the structures and manufacturing lead. We probably handle the bulk of
what goes into actually creating the rocket.
I'm Jaden Webster. I was on the structures team and I'm a sophomore here at KU.
And my name is Rudresh Prabhakaran. I'm also a sophomore here at KU. I work under Connor in the structures team.
A lot of the design processes were managed by the manufacturing design team. We had to plan out and manufacture each part, which ranges from metal parts to composite parts to prints, anything like that needs to go into the rocket. This year we really leaned into the sort of trying to research everything that goes into the rocket and justifying why we're making changes. So we tried the new method of laying up on a mandrel.
One of the professors that we were studying under suggested, hey, if you're making a tube, why don't you try laying a carbon fiber in a tube shape?
We went with carbon fiber because of its great strength to weight ratio. With that, it's 6 layers of composites. KU's known for working with composites, so we figured we'd dip our toes more into that.
So we use the respirators and we make sure we do it outside in a safe space. We make sure to adhere to them as strictly as we can.
The design of the fins has kind of changed a little bit.
Basically, if you go too fast and your material is too thin, what will essentially happen is your fin will start moving around, flapping back and forth, and that can quite literally rip it out of your rocket. That was a large goal of ours to avoid that this year.
So we just opted to purchase pre-laid up carbon fiber sheets that we're going to cut the fins out of. So the nose cone was 3D printed for rapid prototyping. For the actual launch, it'll be fiberglass. The fiberglass doesn't have to be as thick as the 3D print, so it'll allow more room for the electronics.
My name is Kris. I am one of the co-leads on the electronics team for Argonia this year.
Hi, I'm Belle. I'm also one of the co-leads for electronics for Argonia this year.
So we were in charge of creating the system of electronics that had to go inside the rocket. This included a GPS, a flight computer, and
a receiver. So we got some new technology, the Blue Raven altimeter.
The Blue Raven specifically we chose because it came with an app that we could use to essentially code everything in our flight computer.
So we get to punch in most of the numbers and it can simulate the data for us, all of the rocket launches, and we could test out the rocket to see, oh, does the igniters work at a certain specific time that we had programmed them to do so.
Our flight computer was in charge of measuring flight data, things like the apogee and burnout and the velocity of the rocket. The flight computer used this data to do our stage separations.
I was really happy that the Blue Raven had a part in its programming where we could program it to shut off or not ignite if the Raven was tilted too far one way.
So our flight computer had a built-in feature to be able to comply with the safety features that Argonia required. Obviously, the location of the electronics is really important. For the GPSs, we have a 2-stage rocket. Because of that, we needed 2 separate GPS components, one in each part of the rocket. That means they each required their own battery, and that had to fit inside a very small diameter.
I'm Sam Brower, a sophomore and the sub-lead for payload section.
I'm Sammy Masello. I'm the co-lead for the payload team.
Our team, we designed and built the payload section, which houses the electronics in flight and to keep it safe on its descent.
Just make sure that the parachutes are well protected. You also have the golf balls to consider, all of the different constraints, working with the different teams. You get to work with the structures on the dimensions of all of the tubes, and then you get to work with the electronics for all of their different housings. You just basically get to work with everyone, making sure that all of the constraints fit to how they need it to be. The parachute, shock cord, any of the payload, electronics, so we want to make sure that all those are protected. Our tube width is 2.5 inches, but the housing for the booster, because of the coupler and a couple other things, it goes down to 2 inches. We also have a couple of constraints with how tall everything could be, especially with the electronics and what we have in the payload of the rocket.
I'm Tyler Ackerley, and I'm the president of the Jayhawk High-Powered Rocketry Club.
I'm Raymond. I'm the treasurer for the High-Powered Rocketry Club. We're both team advisors, so I mainly overlook the electronics team and helping out.
The biggest focus in most aerospace applications is always safety, so that's kind of where we've started. And I've been working really closely with all the faculty here at KU to make sure that the processes that we're using to make our rocket are actually safe and fundamentally sound.
So the question was, is there anything that you're proud of with this project?
Some of the things that I'm proud of has been the amount of firsts achieved with the club, with first ever two-stage rocket in the club's history.
And we did have the first successful metal mandrel layup at KU. So that was very cool and made me pretty proud.
It hasn't been accomplished consistently at KU for as long as I've been here. The patented process, we'll say, is state of the art and works really well. So we're really proud of that.
Yeah, I mean, I'm very proud about our electronic. This year we upped our budget by a lot, and that really helped us get going with actually making our electronics and testing them. Last year we weren't the finest with electronics as our first year doing Argonia, but this year we really ramped it up, and I'm really proud of the team.
So this is KU's second year doing Argonia. There was no real baseline, nothing to work off of concerning electronics. I'm really proud of the system we created and that it works for the club's first ever two-stage rocket.
Honestly, seeing the rocket fly was one of the coolest things.
It was a pivotal moment when we had our first test work, right?
And being able to say, I built that.
Having a rocket that worked as compared to last year was great.
And the level of teamwork and camaraderie that's happening in the team itself, 17 members total, has been really nice. Argonia test launch in 3, 2, 1, ignition!